My name is Toke. I work at Red Hat on networking stuff, and I'm going to talk to you about TCP. And so this is probably a topic that has a very varied audience, or like when I was doing this talk, it was very hard to figure out how much detail to go into, so I opted for way too much. But just sort of to get started, let's do, just to get a sense of how much do you actually know. So let's do a show of hands. When I say something, put up your hands and then keep them until I say something you don't know. So, how many have heard about TCP before? Excellent start. All right. How many can explain how the TCP handshake works? Okay. How many knows what SAC is? DSAC? RAC? All right. How many can explain how the BBR congestion control algorithm works? Oh, it's just Jesper now. Damn it. Okay. How many can explain how TCP zero copy works in the kernel? God damn it. Okay. Jesper is going to be bored for the whole talk, but for the rest of you, my hope is that there will be parts of the talk where you will go, oh, I already know this, and parts of the talk where you go, oh, that's new. I also have around 50 slides for 55 minutes, so I'm going to go through them relatively quick. And the way I figured we could do this is that feel free to interrupt me and ask questions or go into details, and that will sort of determine which parts that we will spend more time on. That's your question. So feel free to do that, and if we run out of time, the slides will be there for you. So I have a bunch of stuff on the agenda. We will go through the basics of how TCP starts up its connection, the different loss recovery mechanisms, how congestion control works, how TCP interacts with the other parts of the network, different measurement tools and techniques you can use to look at your TCP stack, and talk a little bit about TCP zero copy at the end if we have time. So let's start with the basics. TCP. It's a connection-oriented protocol, unlike UDP. So you have to connect. It's byte stream based, so you chop data into packets, but you don't know. So you just send a stream of data, and the kernel or the TCP stack decides how to chop it up. This can trip people up because often when you just test, whenever you send a bunch of data, it will go into one packet, but that's not guaranteed. It's reliable in the sense that it will keep retrying packets until they arrive, or you will get an error. So you can depend on, okay, if I send traffic into the TCP stack, it will come out the other end in the same order. It's adaptable, so it will try to figure out how much bandwidth is on the link and use everything, and that can be a problem in itself, as we will see. It's also really old. RFC 675 was published 51 years ago. I think it might actually be 52 now. So it's probably around the median age of this room. But it's the same basic principle that has adapted a lot, which is also why some of the things that have some of the developments shows its age, you can say. But a lot of you already knew this, but a TCP handshake just goes, client sends a SYN, server goes back with a SYN ACK, and then finally you have the ACK, and now you're going. So this is, as you can see, these are small packets. It's very much RTT dominated, so it doesn't matter how much bandwidth you have. This is going to be the RTT before you can even start sending. And then today, obviously, we like to encrypt everything, so we add TLS on top, and suddenly you have, this is the TCP handshake, and then you have another couple of round trip times just to negotiate TLS. So if you have, you will have hundreds of milliseconds in this example of an RTT around 70 milliseconds, which whoever did this on Wikipedia picked arbitrarily. But it will be quite a few round-trip times before you can start sending data. And in this, for example, for a web transaction, before these are very short connections, this can actually dominate how much time you spend on your connection. So this is the important thing to do. If you're doing small connections, this also applies to RPC loads, for example. this is dominated by RTT, and it can take longer than the data transfer, because in one RTT you can send megabytes of data on modern networks, but you still need to do the handshake. So this is also something to be aware of when you're designing applications, to focus on the latency and the round trip times as well. All right. Loss recovery. So, as I said, TCP is supposed to be reliable. It has a bunch of mechanisms to ensure that this happens. The simplest one is just you send packet 1, that comes back with an ACK. You send packet 2, that is lost. Then you wait for at least 1 second, but more if your RTT is more than, so that this formula goes above 1 second, but it's at least 1 second you wait, a timeout, and the sender will retransmit. In modern networks, 1 second is forever. So obviously, you don't want to hit this. This will also get you all the way down to sending really slow. So we have something called fast retransmit, which is also pretty old. It's one of the things that was added in the 80s and 90s, I think. So if you have one packet comes through, gets ACKed, one packet is lost, 3 more packets come through, and they get ACKed. So the ACK is always the furthest along the sequence number space that you are. So you have 3 duplicate ACKs that says, oh, that's a loss, so I will retransmit. That's the basic thing. Most people have heard about these things. But then you have more stuff. You have SAC and DSAC, where you can go, I've lost packet 2, so when you send the second ACK, you can go, oh, I have SAC for the third packet, so the sender knows only to retransmit 2 and not 3. And I forget right now what the D in DSAC is, so you can go and read the RFC. All these RFCs, these are links. If you look at the slides, by the way, they're very readable. You can go and read them. They're probably also, the low numbers are still decades old, so yeah. Then you have tail loss probes. This is one of the newer additions, because as you saw with this one, this works if you have another packet coming, but often you will get loss at the tail, because you send a burst of packets and the last one will overflow the buffer and it never gets through. So this is a sender-initiated probing mechanism that was added to TCP. I think this came out of Google, actually, because they have a lot of, they serve a lot of web traffic, so they discovered this. And this only waits 2 RTTs. So if you have a 20 millisecond RTT, this is 40 milliseconds instead of 1 second. And it only triggers if it's the last packet that was not triggered. And then it will just sort of retransmit without waiting for anything. And hopefully that will just get an ACK. And also it doesn't reduce the window, so it's just this, oh, maybe the last packet was lost, I will just retransmit it. And it's a little bit extra bandwidth used, but when it works, it really helps with getting the connection through. And then there's RAC, which is pretty recent. You see we're in the almost 9,000, so this is only a couple of years old. And this is one of the new things when I was doing this presentation that I discovered. I didn't know what this was either, but it's a thing. This is when you hear TCP folks talk about the modern TCP stack doesn't care about reordering. This is what they mean. So what it does is it keeps a recent window based on the RTT. So the minimum RTT divided by 4. So again, if we have a 20 millisecond RTT, this is 5 milliseconds. And any out-of-order packets that arrive within this window do not trigger any retransmissions or reordering, all the mechanisms that TCP usually have. So usually what happens if you reorder packets is that if you go back to this one, if this was not lost but just delayed, you will still get 3 new packets and you will get dubacks and you will trigger all the retransmission mechanisms. But if this just arrives a millisecond after these ones, with RAC you keep the reorder window and you don't trigger anything if they arrive. So if you have, say, an ECMP link, which is pretty common, or some other, even just reordering in the stack, you have a load balancer that takes 2 different paths through the stack, or you rehash and go into a different CPU or something, and package get processed out of order. You don't care. You just keep going, and you notice that this is within the window, and TCP just works fine with reordering. And this significantly improves the behavior when the network reordering packets, to the point where these kinds of, there's a lot of old middle boxes in the network, for example, that try to, thou must not reorder TCP because it will kill performance, and that is no longer true all the time. So that's something to be aware of as well. And of course, this requires you to have a Linux stack that's newer than this, but yeah. So just to be aware of all the different mechanisms that are in play for loss recovery, and some of them can really improve behavior, especially for reordering. But this is also a moving target, so it's a good idea to check your assumptions once in a while, especially if you're building something that interferes with the TCP flow through the network, like a middle box, but also just when you're designing your application. And there's also, especially in the Linux TCP stack, is improving a lot, so keeping up to date with that is useful. All right, and then there's congestion control. This is also one of the big, I think this Wikipedia list of other algorithms is quite long. A lot of them have been research projects that never really went anywhere. I think there's at least a dozen different ones in the Linux kernel. You can do them in BPF now. I suspect these may also be target of code removal now that everything is a liability. But I will just cover the three most used ones. So the function of congestion control, as I said in the beginning, TCP will try to scale up to any bandwidth that it wants. And when it did this back in the 80s, we had something called congestion collapse, where nothing could be sent across the internet because every time you tried to transmit something, the network was so congested that that nothing got through, and you would get into this retransmit loop, and everything, it was a feedback loop that just killed the internet to the point where it had to be manually rebooted, basically. And after this, congestion control became a thing. And basically what TCP congestion control does, it's driven by the sender mostly, and it reacts to one of these signals. So packet loss, as we saw, duplicate ACKs, or just retransmission timeouts. ECN notifications was also a thing I won't go into so much now, but you can set a bit in the header that says congestion instead of dropping the packet, and TCP will also react to that in various ways. And some congestion controls also look at the RTT itself, because if you have lots of buffering in the network, an increasing RTT is a signal for congestion, even though you won't get drops, which is also a problem in itself that we will come back to. So this is the classic Reno TCP textbook example of how a TCP works. This is time. This is the congestion window. So that's how many packets that TCP will send at once before it waits for ACKs. And so it's sort of this ACK clock feedback loop. This one is 2 packets to start with. Today you can also have 10 at IW10, this is called, which means you will just, any connection, you'll just send out 10 packets at line rate. And as you can see, this is exponential, right? So when people say slow, that's why slow is in, I think slow means exponential in this case, but it's slow relative to just sending at line rate from the beginning. So that was from the congestion. And it will sort of go up. You send 2 packets, you ACK them, you send 4 packets, they get ACKed, you send 8 packets, you get ACK, and so on and so forth. And you just keep doing this until you experience loss. And then you say, okay, I got this far before I had loss. I will go back down, and then I will ramp up to this point again, and then I will go into this new mode of congestion avoidance, where I will slowly probe for more bandwidth, but this is basically the steady state. Most literature you see about TCP throughput only deals with this bit. Most, say, web traffic on the internet, for example, never leaves this state. Because as you can see, at this point where you've up to 64 something packets, that's kilobytes of data. So, well, maybe not a modern web page, but this used to be the case that you can fit a whole blog in that, right? So this ramp up and down, and then this linear steady state behavior is the standard congestion control and congestion avoidance that you sort of see in the literature. But actually, most applications run something different. So the default in Linux is TCP cubic, which is standardized relatively recently, but it's been the default in Linux for way longer. And it's also the default in Mac OS X, and it's in Windows 10. It's more aggressive, but it's still fundamentally the same. So instead of having this exponential ramp up and then the steady state, it does, yes, it still reacts to the same things, as things, but instead it does this, which, as you can probably see if you remember your high school maths, this is a cubic function, hence the name. So it sort of does the same thing, except it fits a cubic function so that the steady state becomes this thing in the middle. And what this does is that instead of having the linear ramp up that you have in TCP Reno, which is really slow, if you actually, like say you're sharing the link and suddenly the other person goes away and now you have double the bandwidth. If you're ramping up one packet every RTT, that will take you a while. Whereas with cubic, you will sort of go and then suddenly you will get out here to the concave part of the cubic function and you can ramp up way faster. So, but other than that, it's basically the same, so you can think of it as a more aggressive version of Reno TCP. And this is the default in most cases. Except, then there's these people at Google who serve a lot of web traffic and video traffic. And they discovered that cubic has this problem that it's still loss-based. So if you have lots of buffering in the network, it behaves terribly. And your video will bzzz, and you won't go anywhere, and people will be sad. So they have a whole research team. I think, oops, oh no, what did I do? Most of the TCP development in Linux is also done by Google these days. Where did we go to? Yes, so they came up with this BBR. I can't expand the acronym. It's something better bandwidth reduction, something, I don't know. Look it up. But it's doing something completely different than what cubic and TCP is. Cubic and TCP are this, well, there's an algorithm, it reacts to events in the network, so on and so forth. BBR tries to model the link behavior, so it has this baked-in assumptions of how a link behaves, and it takes a lot of input from what it observes on the network. And it tries to build a model of how to behave. And especially the first version, which is the version that's in Linux, only reacts to timeout and RTT increases. So for one thing, it completely ignores loss. It completely ignores ECN notifications, which was one of the things after it was upstreamed that got a lot of attention. There's new versions. There's a BBR with 3, which takes everything into account, but that's not in upstream. So if you know someone at Google, go and bug them to put it upstream. I do that with occasionally, and it hasn't helped, but maybe if we are enough people. But basically what BBR does is that it has this cycle where it goes, I think this is normally a, well, here it's only a few seconds. Okay, so it sort of does a steady state, and then it occasionally probes for more bandwidth. So it sort of, this is the rate I'm at. Every couple of seconds, I will try to increase my bandwidth, and I'm mostly looking at the RTT. So if the RTT goes up, there was no more bandwidth, I will go back down. But if the RTT does not go up, that means that it's that I'm not hitting a bottleneck, I'm not getting queuing, so I can keep doing this. And it does this sort of, it has this occasional probe mechanism, which you can see experimentally. We will get to that later. So this is just a completely different model of how TCP works. And it's the default on YouTube still, I think, BBRv3. So also just to be aware that if you're running a middle box or a server against something, you cannot necessarily rely on anything. So, important points. Classic New Reno is what you hear in the literature. It's a complete fabrication. Cubic is actually the default, and BBR is totally different. Also, just a little, this is how you do things in Linux. The allowed congestion controls, that's just all the modules that are loaded. And available is the ones, available is the models that are loaded. Allowed you can change so that you disallow some. There's a socket option to set it per connection. And then the TCP congestion control is the default that is used if the application does not request something else. So you can tune this on your system, you can play around with it, it's fun, I promise. Right, any questions so far? Anything, are you bored? Are you still awake? Yes? TCP 6? You mean TCP? What, TCP over IPv6, you mean? Yes. So TCP completely doesn't care at all whether it's IPv4 or IPv6. Not by default in Linux. It will do the same thing for v4 and v6, but that can be, like for example, some of the routers can behave differently depending on the protocol. So for example, some routers don't understand ECN in v6, but they do in v4. You can have different bugs. I've seen ECMP being broken in v6, but not in v4, for example. So there's a lot of sort of behavior, but in principle, in the code, the TCP stack doesn't care. But the network may be broken in different ways depending on your protocol. So I think that would be my guess. Yes?
Just take the box.
Hello. So I'm wondering, is this a client or server side, or is this the sender side or receiver side? Do they need to cooperate, or is it only the sender where this is?
Right. Yes, good point. I should have mentioned that. So congestion control, in most cases, is completely driven by the sender. And this is also a coordination problem, right? That the sender controls what it's sending, obviously, and it's just getting ACKs back, and that's the information it gets from the network. There do exist, some of the algorithms can be receiver-driven. There do exist some schemes. Like the receiver has one knob it can do. It has a receive window where it says, this is the amount of data that you're allowed to send me. And there are some schemes that will try to and this can vary, like normally it's just used to make sure you don't overflow the memory of the receiver. But there are schemes that will try to signal, to get the sender to slow down by scaling down the receive window. But they're not, these are mostly used in closed, like in data centers where you control both endpoints. You can do various receiver-driven things. There's also something called data center TCP, which is another congestion algorithm I haven't mentioned. So but over the internet, it's very hard to rely on this, so it's mostly sender-driven. And that's also why Google can deploy BBR without caring what the receiver does.
Thank you. What do I do with this now?
Throw it down there, that's another question.
Are you prepared?
Nice.
Hi, Eric here. I was thinking about, I listened yesterday actually to Axis. They were doing a similar thing in video codecs. So they had a modeling outside of a codec, but kind of helped the codec to perform better. Is that an analogy to what BBR is doing?
Yes, I think so. There's also a whole interaction between exactly streaming video and TCP. So there's various congestion control algorithms for video, which sort of work differently, similarly, because usually when you can stream video over TCP, and if you do like YouTube or something, that's not actually streaming, that's downloading chunks, so that's TCP. But if you're streaming video from a camera, for example, it can also just be UDP, and it has to do its own congestion control. And sometimes you have the video that's doing congestion control, and then it's sending it over TCP, so you have two different congestion controls fighting for control, and that can give some really nasty things. So I'm without knowing exactly what you're referring to, I would say it's probably similar.
My point is that instead of conceptual thinking of it as another layer of a stack, it's a outside modeling that kind of directs the performance of a stack.
Yes,
yeah.
And I think also because for streaming video, you have this problem. If you just use the congestion control, the video will keep producing more data than you can send, so you have to also scale down the video. So that's why, for video in particular, you get these interactions.
Anyone else?
Another sort of thing where gets really weird is if you have TCP over TCP, and you have two different congestion controls on the two different TCP connections, you will get some really weird behavior as well. Right. So for example, OpenVPN has a TCP streaming mode, and that usually doesn't perform so well for that reason.
But like, there's so much, but you have like the two different
So if you have, so the question was, what if the two endpoints have two different congestion controls? So usually, because it's sender-driven, that means that traffic in one direction will behave differently than the one going in the other direction. But you don't, unless you do weird things with the receive window, you don't control what data you receive. That's only on the sender. So if it's two different ones, which you can totally have, that just means that traffic in one direction will behave differently. Yes, yes. Yes, yeah. So the question is there an advantage to doing things differently in different directions? And that can be the case. For example, on a home link, your connection is usually wildly asymmetrical. Not so much anymore, and especially not in the land of fiber. But like a DSL connection can have a like 10.1 or 110. So you can have advantages of doing things differently. Like, for example, BBR was developed to avoid buffer bloat, which I will talk about next. And that's more important in the upstream direction than in the downstream. So depending on your application, and depending on whether you can actually control both endpoints, this can be something, like it can make sense to have different ones in different directions. BBR v1 is upstream. BBR v2 and v3 live in a Google GitHub repository somewhere, so you have to patch the kernel. Yeah. Yes, one more.
Yeah, when you say changing bandwidth, is it like changing the package size or timing between packets or something else?
Right, so it's usually the timing. It can be both, but usually, so most of these examples assume that you have infinite bandwidth stuff to send, right? You don't, so a connection can be application limited. If your web browser doesn't produce anymore, you still have the connection, but you don't have any more data to send. Most of these examples was just, I'm downloading a big file, so I'm just trying to send data as much as possible, and what it is varying then is the space between packets, yes. So usually you will try just to use the network as efficiently as you can. You will send maximum size packets that you can. There's a whole different topic of path MTU discovery, where you, if your local link has a larger MTU than a downstream hub, you can send a big packet that never gets through, and there's probing mechanisms to do this, which sometimes work. Or you can configure it manually, but usually when the TCP is just sending data, it will just do as big packets as it can. All right, so we sort of gotten a little bit into this already, so I'll talk a little bit about different interactions, because as we've seen, TCP is not just the same on its network, and we have these, a lot of the modeling assumptions are also just, this is all just the fluid dynamics, packets just go, and we don't have weird behavior in the network. So, and in practice, weird things can happen with TCP. So one thing, the first thing is, I've already touched a little bit about latency. This is the pretty old graph, but I couldn't find a new one. So just the main point still stands, that like the numbers are a bit low, as you can see. But so this is for page load time. And as you can see, with more bandwidth, you don't necessarily, like to start with, you get a lot of increase, but then it's very much diminishing returns for page load time in the web. The actual numbers will be different today, but the principle is still the same. Whereas with RTT, it's just linear. So RTT actually matters a lot for interactive applications, especially as bandwidth since then has only exploded. Like if you have a gigabit connection and you're surfing the web, you're not using all your bandwidth, and going to 10 gigabit will not help you. But decreasing RTT will, because we saw in the beginning, you still have to do the handshake, you have to do the TCP connection, and you have to go and request something that will then come back really quickly. And there's been sort of various innovations to try to pipeline stuff and so on, but sort of essentially, if you have an interactive application, you're waiting on the user. So when the user clicks on something, at least you have to communicate with the server. So RTT is more important than bandwidth, once you have enough bandwidth, and enough varies by application, but it's less than you think, basically. Like 4K streaming is less than 10 megabits per second, if I recall. Maybe it's 20. But above that, like, it's very hard to use all this bandwidth for normal applications. What you can do here, and one of the things about latency is you have this thing called buffer bloat. This is one of the original graphs from back when I did my PhD about this, where it's over time. You start a ping, 5 seconds later, you start a TCP connection, and the ping does this, whee! 800 milliseconds of ping. It was fine before you started. And what happens here? This is all buffering. This is just queuing delay. And it was there all the time, but doesn't show itself until TCP starts up, because TCP will scale up and it will use all your bandwidth. And if you have hidden buffers, you will see them. This was buffer bloat as a phenomenon, was first discovered, what is it now, almost 15 years ago. FQ Cuddle turned 14 a few weeks ago. So, and it's still there. Sometimes it's gotten a lot better, a lot of stuff has happened, but you can still have this. And TCP will find this if you try to run a flow through it. And this, as we saw before, RTT is really important. Now RTT is crap, so your application is crap. And basically what this comes down to is that loss or ECN marking is actually an important signal. TCP will keep ramping up until it gets a loss event. So if you just buffer packets and don't drop them, you will tell TCP to keep ramping up. And this is exponential, so it will keep going. And if you want good behavior and while scaling TCP, you have to have this timeless signaling. So the late Dave Tart had this riff on the Monty Python song where he got every packet is sacred as sort of a way of making fun of that. So don't do that. Make sure that you actually signal your endpoints so that they can function smoothly. You have various tools to do this. You have active queue management. You have vanished queuing, which you can deploy. It's the default in many places, but these are tools. If you want to hear more about this, come talk to me. I have a book to show you. Also, link layer retries can add latency. Wi-Fi, particularly if you have bad behavior. We've tried to fix drivers. Some of them will still retry 30 times, I think, before giving up. And this interacts with the next thing, which is head-of-line blocking. So TCP is stream-based. So if you have this drop and you have the retransmit, you will not get even though the receiver already got packets 3, 4, and 5 here, the application will not get them until the retransmit. So you get this head-of-line blocking where even if you only lose one packet, from the application it looks like it's incredibly bursty because you will just do the receive call and nothing will happen until the retransmit has prepared things, and then you will get lots of data. So this is a thing. Some applications get around it by opening multiple connections so they don't interfere with each other. There's also the QUIC protocol, which has this built in. So there's various ways, but just sort of if you multiplex different things over the same TCP connection, you're going to wait on yourself if a loss happens, and loss will happen. There's also this TCP hardware offload. Various NICs have various features for for offloading things. So in most of the models and the literature, you will see, oh, packets, it's smooth. Like you said, we just vary this time between packets, but it's sort of spaced out. But then you have these things like servers using TCP segmentation offload, where the network stack just sends 64K at once, and down into the NIC, and the NIC will chop it off into MTU-sized packets and send them out all at once at line rate in your data center. So, and these will all go out one after another, and you will have one burst that hits the Wi-Fi link at 2 megabits per second. And then we get the graph we saw before. So this sucks. It doesn't, IW10, initial window 10 package can do the same at a smaller scale if you have very low bandwidth. But this is also just something to be aware of, that your mental model of things being smooth is also a lie. We have this thing called TCP pacing that tries to actually do something about this, which is a nice feature that also got into the Linux kernel. The FQ QDIST will do this by default with the TCP stack, where the TCP stack sort of has this internal notion of how much bandwidth do I have, and it can actually space out the packets. And with hardware assist, it can do this by just attaching a timestamp and say, telling the hardware, please schedule this and please space out the packets so that they fit with the bandwidth I actually want to use. That helps with the burstiness, and it can also significantly reduce performance if you have these burstiness leads to buffering and so on and so forth. It does hurt aggregation wireless links some. On the client side, there's some mechanisms to help with this, but just also something, it's all trade-offs. So, just something to be aware of. TCP interacts with layers in weird ways. Latency is very important. Congestion signaling is important. You will always fill your buffers if you use TCP, so don't make sure to manage your buffers and be aware of how the hardware actually behaves. Right. So I will go through some measurement tools and techniques that you can use to peer into how TCP works on your network, how TCP works in Linux. And I just collected all of them on this slide. I'm not going to go through all this. These are all links, so we'll publish the slides somewhere afterwards. You can go and click on them, but you have your basic throughput tests. You have some latency tests. This one you definitely know. These are some of them you may know. You have some application level tests. You have some utilities that you can go in and look at how the connection actually works. These are web-based public speed tests that will also give you latency figures. And then there's some integrated tools for running more sort of comprehensive test suites. I have some examples of how some of this works that I will go over quickly. You can look at the slides afterwards to see how they are, but it's also just to give you sort of a comprehensive list of various tools that can be useful. So one thing that's a really neat thing is this SS utility, which lives in most Linux distributions ship this by default. I think SS means socket stats. And what it can do, so this is showing you TCP. This also works for other things in TCP, but this is just showing you TCP, and the I and P in particular shows you what a lot of internal information and the process. And then I'm just saying, okay, show me the netperf processes on machine. So you have the netperf pit here, and then you have, this is using BBR, and then you have all this information about the internal state of the TCP flow. I think these are these might be the two flows in two different directions. You can also, it's established and it holds. So you can sort of monitor this and figure out what is TCP doing, right? This is the RTO timeout, this is the RTT that it has, this is the path MTU, how many segments, how many bytes has it sent, this is the internal BBR state machine, the pacing gain, all this stuff. So you can get a very deep insight into the various aspects of your TCP connection. Of course, again, congestion control mostly runs on the sender, so this makes the most sense for traffic that's going out. TCP trace is an old and venerable tool. The latest version is from 2004, but it still works. It can take a PCAP file, it can trace it, and then it will find all the connections that are running here, and it will do various graphs of them, and it produces XPlot files that you can then run and explore. And one of the things it will do is this time series graph, which I gave up trying to get screenshots for this because it's a really old application. So it does work still. Wireshark has something similar. So this is the same time sequence graph that the TCP trace does. And this shows you over time segments over here. So the bottom line is that's the receive window, and that's the congestion window, and these are all the packets being sent. So you can see, okay, here a packet was sent, so this increases the number of outstanding bytes, and then it gets ACKed, and you can see all this. And this is, it will also show you if there's a drop, it will show you a little cross, so you can see retransmits all this stuff at a packet per packet levels. If you want to go deep into why is TCP misbehaving, this is a good tool. Wireshark can do this graph and a couple of others. TCP trace has more graphs, but it's basically the same. So if you go in and you look at detailed packet graphs. Then there's Flint, which is my own tool, so of course I have to show you that. This is a wrapper tool around NetPerf and other utilities where you can run, say, this is a TCP2 up pre-canned test that will run 2 upload tests, and it will show you it ran at 25 megabits for each flow, and it collects all the stats over time. And you can plot it over time as well, so you can see the RTT and the bandwidth for the different flows as they go along. There's a lot of pre-canned tests for you can show them, you can zoom around. This is a nice way to doing these performance tests of especially behavior under load. You can also plot the SS output we saw before, it can also capture, and you can plot things like the TCP window. So here you have the cubic function that we saw before. You can actually see that in the congestion window. And here we have the BBR probe events. So, I should go probing. So you can actually see the behavior of the different TCP algorithms when you make plots like this. So, lots of different throughput testing is a good first step. You can measure latency as well. Do it under load, please. You can do deep dives into TCP behavior by various ways. Integrated measurement tools can be helpful. Speed tests actually have these latency tests, so go and look at those as well. And we have time for TCP zero copy. I think I have 10, 15 more minutes, right? All right, it's going well. So, TCP zero copy. How many have heard of this? Okay, about half the room, pretty good. So, I won't go into too much detail about this, but it's also something to make you aware of. It's a feature, so normally when you have, this is all about how data gets from the network into the host. So normally the flow goes like this. You have package coming into the NIC. The NIC DMAs data into the kernel buffer, and user space calls receive or receive message, and it will get a copy of the data out into user space. Similarly, when you send something, user space will prepare the data it wants to send in a buffer. It will call a kernel syscall, which copies all the data into the kernel buffer, and that runs the TCP stack, and eventually it's DMA'd into the NIC. So normally you have 2 copies of data, one with the DMA'd into host memory, and then one more from the kernel to user space. So zero copy is about, as you can probably guess from the name, zero copy is about going from 2 to 1 copies. So what it does basically on the receive part, it turns it into this when the NIC will DMA data into 2 different buffers directly. So it will split up the data and say the header goes into one buffer that the kernel controls, and the data goes into a different buffer that user space controls, so that you eliminate the kernel to user space copy. And obviously this gives you efficiency by not copying data around in memory. Similarly, when you transmit, user space can prepare its data, and that goes directly to the NIC, where the kernel sort of goes in the middle and runs the TCP stack, builds the headers, does scatter, chops things up, and sends it to the NIC, but without copying the data at all. So that's one feature. You can get your data directly into user space. This obviously, I will get into how it works, but there's a lot of setup needed to get this all to work. So don't do this for small transactions. I think the patches that added this to the kernel said break even is in the several megabytes. So if you have a large file chunk of stuff, you can gain something from this. Another interesting feature that it can also do is that instead of doing this, it can also do this, where the DMA does not even go to user space. It goes directly to your GPU or your storage. And similarly, user space can prepare a buffer that just refers to some data on your GPU or your storage, send it to the kernel, it will assemble the headers, and it will DMA it directly. So it doesn't even go to the CPU. And this has even more potential, of course. If you say, I don't know, are running a big model that has to go into GPU memory that some people like to do these days, or if you have storage that you need to transfer from one device to another and you don't want to copy it into host memory, it also, so this will basically instrument things to go directly over the PCI bus from one to the other, so it doesn't even, the CPU doesn't even see the data. And the way this works is you need some features from your NIC to do this. For TX, you obviously need to have scatter-gather support, because the kernel will sort of assemble an IO-vec that says, here's the first chunk of data, that's the header I just assembled in kernel memory. Here's the next chunk of data, that comes from user space, or it's even on the GPU. And then it sends that to the NIC, and the NIC needs to assemble these into one packet on the wire. That's relatively common, at least for the for high-end NICs and for use with user space memory. For RX, you need the reverse, basically, reverse gather, I guess you can call it, which is called TCP header split. So the hardware needs to understand TCP, it needs to pass the header and be able to send the header and the data to two different memory buffers. And the kernel does all the bookkeeping to tell the NIC which buffers to use, but the hardware needs to support this. And then you need, for the driver, for RX, the way this works is we have this page pool memory, network memory abstraction it's turned into. It started out as a performance optimization that Jesper did for XDP, and now it's basically the underlying memory management subsystem for the whole network stack, for high-end NICs at least. And it's basically a SLAP allocator specialized for this. So it will take whole chunks of memory, and it will cache them and reuse them so that when you get packets coming in, they're available really quickly. I'm simplifying a little, but go talk to Jesper if you want the details. And so what this zero copy basically does is that says, okay, I will allow user space to give me a chunk of memory that is used for packet data, and I will instantiate a page pool that manages this user space memory, or device memory, as it were. And I will just use that to give pages to the NIC to put data in. And from the driver point of view, as long as it's using page pool and it implements the right APIs to swap out the whole page pool it's using, the driver doesn't need to do anything else. So that's pretty neat. It's just a complete abstraction of a memory where the driver just goes, give me a page, and the page pool will go, oh, here's a user space page, or here's a device memory page, and things will just continue to work, which is pretty neat, but it's pretty new also. So I think there's 2 or 3 NICs that support this in mainline now. If you have a NIC, write some patches. So what does the application have to do to make this happen? For TX, it's actually pretty easy. You just send message zero copy, and that's it. You're done. The kernel will then go, okay, I will take this buffer and I will send it directly to the NIC. And if I can't do that for whatever reason, for example, the NIC doesn't support gather, or there's some other reason why I can't, it doesn't fit, it's unaligned, some weird thing, it will just copy. So it sort of has a transparent fallback to just copying. But if you do things correctly with the right amount of data that you're sending at one time in aligned, you can just do message zero copy and it will get copied. It does, as I said before, it requires a lot of bookkeeping in the kernel. So for one thing, you have to keep the buffer around, right? You send it a chunk of memory, and if you write to that memory before the kernel is done with it, the new writes may or may not go out on the wire. So there's like a receive message error queue, which has now just become a metadata queue. That you can do, and you will get notifications back of this buffer's done, and until you have that, which also includes retransmits, by the way, right? Because if the kernel keeps the buffer around until it's been acked by the other side. So you have to keep it around, and when you get, okay, this one is done, then you can reuse the buffer. So you have to sort of restructure your application a little bit. That's relatively simple. You can also use IOU-ring to do this, which is a nice API in my opinion, but that's a detail. You can read this blog post or have some links in the next slides for all the documentation for this. For RX, it's Yes, I'm. Yes, I believe you. So I will repeat it for the mic. He's saying the networking stack is reinventing things and doing it wrong, and it's really broken, which I believe. This is also a very send message, receive message. It's a way to sort of graph things onto the existing UAPI without having to design a new one, and it's horrible. Use the IOU ring one, it's better. I don't think it solves your problem for internal users. But yeah, I agree. This is a horrible API, and the internal bits are also reinvented for the networking stack.
And this is actually a huge issue for the in-kernel usage because it just does not fit with the event model all the basically in-kernel consumers of networking, which is storage devices and file systems have. So there's just a huge impedance mismatch, and Dave Howells is kind of trying to paper over it, but keeps failing because the networking stack underneath is so broken. And also leads to a lot of weird duplicate code because the magic falling back to not zero copy doesn't actually work for the in-kernel APIs, and we tried to fix it, but the networking maintainer insists that's a stupid idea, so I'm kind of surprised he did it for user space.
Okay, interesting. I did not know that, but
Jakub is very, very opinionated on that.
Okay, yes, he's opinionated on a lot of things. I didn't realize this one in particular, but you know, storage and networking are two different communities that like to invent things, and I agree, we should do something about that, I guess. But anyway, with that note, RX is actually even more complicated from a user space thing, because for Rx, you have to allocate the memory buffer first. Either you just allocate user memory, a map, or you get a DMA buff, DMA, what are they called? DMA FF. DMA buff is the kernel structure for device memory, and you can get a file descriptor in user space that refers to a chunk of device memory, whether it's on the GPU or the storage device. And you allocate that, you have a chunk of memory, a couple of gigabytes, you want to use this. Then you go, there's an API via netlink to register this memory with the NIC queue. So that does this binding where the kernel goes and allocates this page pool instance for that memory to manage it, chops it up into page size fragments, sends that to the driver and says, please use this memory for anything you receive on this queue. Which means you also have to go and configure RSS to steer traffic to this queue, because you don't have any control over when that memory buffer data lands. It's just, I give some pages to the NIC, it will put data into this page, and I will tell you afterwards where it ended up. So you sort of have to say, I will say, for this particular connection that goes into this, that needs to go into this zero copy buffer, I will allocate a whole hardware queue. I will configure RSS so that only the traffic I care about goes into that queue. And if I do this wrong, I will get weird data in my memory buffer. Now well. And that's out of band. The kernel doesn't care. It will happily do this dance, and if you do it wrong, you will just get data that disappears or gets into the buffer and so on. But anyway, once you've done all this correctly, you set it up, then you issue a receive command, either via IOU ring or special flagged a receive message, which does, please give me some data, and you will also get these weird message error queue kind of, again, just use the IOU ring. You will get completions, which has references to the chunk of memory you have, and then since it's still zero copy, you sort of have to do what you do with your data, process it, whatever, and then tell the kernel when you are done with it, and the kernel will reuse the buffer. So this is a bit of a complicated dance. IOU ring can do most things except do the DMA buff backed memory allocation. For TX, you also need to do a register step if you're using DMA buff memory, so there's an additional step there. I put a lot of details into this blog post that just tries to summarize this. I didn't write any of this code, I'm just trying to figure out how it works and see if we can get it to work. There's some more. Thank you. There's some resources here. I wrote some UPerf patches to get that to use zero copy via IOU ring. There's some kernel docs for all this stuff. There's some examples in the kernel tree for using these different things. So that can get you started on this. One thing that's work in progress for me in particular is how to get these various user space libraries that, for example, do the runtimes for running AI models want to use this, and there are layers and layers of abstraction, and I have so far given up. So if anyone knows how to, or is interested in helping with trying to get this into stuff so that you can use TCP instead of RDMA for your big setups, or for storage, all this stuff, please let me know. Was that a yes?
Much nicer abstraction.
If you don't have hardware that does RDMA, basically.
Yeah, but you're talking about AI people that just have infinite amounts of money, so.
Yeah, but so this is for the poor AI people, which will hopefully be all AI people a couple of years from now, but we'll see. Anyway, on that note, further reading about all this stuff, questions, comments, the slides will be available somewhere. Yes. Yes, do I have time? I don't think I have time. So yeah, short note, ArgECN is a sort of newly standardized way of turning ECN into something that's not equivalent to drop, but where you can get a more high fidelity signal, so you can react more precisely to changes in bandwidth. And that's been standardized in the ITF. Patches exist in the kernel, so you can run it. There are operators, this is also called L4S in marketing speech. Some ISPs in the US have started deploying it. I haven't played with it in general. So, so that's a thing that's also happening. Yes. There was one other question up there. Do we have a, yes. Do we have a box?
I think, if I'm correct, Pavel is working on actually on DMA buff support for IO Uring. So
sorry?
Pavel is working on IO Uring support, DMA buff support
yes.
in IO Uring. So
yes.
I guess this thing that you mentioned before, it will land.
Yes, I hope so.
Yeah.
And once that does, use that API. Like the only reason not to use it now is if you need the one. I think it actually supports it on RX, but it doesn't support it on TX yet. So once those patches land, just use IO Uring. It fits with the async model. The other one is annoying, in my opinion. All right. Thank you.